gravity is an attempt to unify two pillars of modern physics, quantum mechanics and general relativity. While both of these theories are incredibly successful in their respective domains, they are fundamentally incompatible with each other. Quantum mechanics describes the behavior of particles at the smallest scales, such as atoms and subatomic particles. It is based on the principles of probability and uncertainty, and it has been tested and confirmed by countless experiments. On the other hand, general relativity describes the behavior of gravity at the largest scales, such as galaxies in the universe as a whole. It is based on the principle of curved spacetime, and it has also been confirmed by many experiments and observations. However, when we try to combine these two theories, we run into problems. One of the major challenges is that general relativity assumes a continuous and smooth spacetime, while quantum mechanics suggests that spacetime is quantized and discrete. This creates a fundamental tension between the two theories that has yet to be resolved. Quantum gravity is the attempt to find a new theory that can reconcile these two frameworks. There are several approaches to quantum gravity, including loop quantum gravity, string theory, and causal dynamical triangulation. Loop quantum gravity is based on the idea that space-time is made up of tiny loops or networks of quantum states. String theory, on the other hand, suggests that particles are not point-like objects, but instead are made up of tiny strings that vibrate at different frequencies. Causal dynamical triangulation suggests that spacetime is made up of discrete building blocks, much like Lego bricks. While these approaches have different assumptions and methods, they share a common goal: to find a consistent theory that can describe the behavior of particles and gravity at all scales. One of the fundamental challenges of quantum gravity is the problem of infinities. In quantum mechanics, particles can occupy an infinite number of states, which can lead to infinities in certain calculations. General relativity also predicts the existence of singularities, such as those found at the center of a black hole where the curvature of spacetime becomes infinite. To overcome these infinities, many approaches to quantum gravity propose a process called renormalization, which essentially subtracts out the infinities and leaves behind only the finite observable quantities. Another challenge is the search for experimental evidence. Unlike other areas of physics, such as particle physics or cosmology, quantum gravity is difficult to test directly because it involves phenomena that occur at extremely small scales or in extreme conditions, such as near the event horizon of a black hole. However, there are some potential indirect ways to test the theory, such as through the study of gravitational waves or the cosmic microwave background radiation. Let's talk a bit more about some of the specific approaches to quantum gravity. Loop quantum gravity is based on the idea that spacetime is made up of tiny loops or networks of quantum states. These loops can be thought of as representing the curvature of spacetime, and they can be combined to create a more complex structure. The theory predicts that spacetime has a discrete structure with a minimum length scale known as the Planck length. This approach has led to some interesting predictions, such as the idea that space has a granular structure and that there may be a minimum possible distance. String theory, on the other hand, suggests that particles are not point-like objects, but instead are made up of tiny strings that vibrate at different frequencies. These strings can be thought of as tiny loops, similar to the ones in loop quantum gravity. The theory predicts the existence of extra dimensions beyond the familiar three spatial dimensions and one time dimension, which could help to explain some of the puzzles of particle physics, such as the hierarchy problem. Causal dynamical triangulation suggests that spacetime is made up of discrete building blocks, much like Lego bricks. These building blocks are known as simplices, and they can be combined to create a larger structure. The theory predicts that spacetime has a fractal structure with different scales of structure appearing at different distances, Overall, quantum gravity is a fascinating topic that continues to challenge physicists and push the boundaries of our understanding of the universe. While we are still far from a complete theory of quantum gravity, we are making progress every day and uncovering new insights into the fundamental nature of spacetime, particles, and gravity. In conclusion, quantum gravity is one of the most exciting areas of research in physics today. It holds the promise of unlocking some of the deepest mysteries of the universe, such as the nature of black holes and the origin of the universe itself. While there is still much work to be done, we are making progress every day towards a better understanding of this fascinating topic.